Hello, my name is Justin Castillo, and welcome to my video for Programming Assignment 1, Parallel Execution. My program is designed to show an understanding of parent-children processes and inter-process communication. I've used a pipe to demonstrate this. My program asks for an input n and spawns that many children processes which complete a unique task, compute an output, and send that output through the pipe to the parent process, which displays their results at the end. Each task was chosen mainly to avoid having to have the user enter input for each task to simplify the illustration of the forking process. The processes or the functions are arbitrary arithmetical calculations that are de-optimized so that runtimes are significant enough or long enough to show that they are indeed running in parallel in accordance with assignment directions. So I put the stubs or the prototypes at the top here, and then define them below, and they're just all simple arbitrary math calculations that I've extended with huge numbers using various techniques to extend the running time to get a result that's comparable. It doesn't just round to 0 milliseconds. So for here, I used a volatile to avoid having the compiler optimize the program by saying, hey, it doesn't ever use the results of this loop, so we might as well not do the iterations of it. The whole point is to show the processing time, so I made that impossible with a volatile. And an XOR makes each iteration do its own little mini calculation. The calculation itself is meaningless, but it's just, again, to extend the running time. And that was, so I just picked, count the number of primes up to 800,000, do 20 factorial like 5 million times, do the recursive version of the 35th Fibonacci number, get the greatest common divisor of super large numbers, and repeat it many times using XOR to make sure that the process doesn't get optimized, and then just doing the summation of a gigantic number. So all of those had running times that are human readable, interpretable. All right, so I'll go ahead and do a live demo for this now. So this is I'm running it in the Ocelot on my Bash terminal here. So it says enter the number of child processes. I'll put 5. All right. So we see that each child has a unique PID. The parent's PID is repeated down here, showing that the parent has the same process beginning and end. The children process in the order chosen by the compiler to start, but I calculated the time of the parent, which is about 572 milliseconds. And if we look, the time of the longest child is 570 milliseconds. So it's very close together, which means that these didn't run sequentially. It's not 85 plus 116 plus 37 plus 172. It's just 2 more than the slowest child, meaning these had to have run at the same time. And the children themselves don't display any results. The results are displayed by the parent. So let's see here. So the overhead, the reason for the extra, 2 or so milliseconds is just because each read-write call to the pipe is a system call, which incurs some overhead with the inter-process communication. So here's a simple diagram showing the parent runs continuously throughout. It forks off 5 children. Each of them computes a result. The result is sent from the pipe to the parent, and the child process terminates where they can be the results can be read and then processed, and the children can be reaped by the parent to prevent the zombie children. So let's see. One issue I faced was choosing appropriately large and inefficient child processes that would take enough time to be able to demonstrate parallel processing. I solved this problem by switching from int output to long longs to get huge numbers, and defining constants, which are also giant numbers, to sort of get the running times in a reasonably readable range. Um, and using a volatile variable to store meaningless temporary results from a loop in the factorial process, and using the exclusive OR in the factorial and GCD functions to prevent the compiler from deciding not to iterate because the end result was never used. Here is my AI chat log. I use it quite a bit as like my own personal tutor that can't ever get tired of me asking the same question over and over until I understand it. So I'm going through the lecture, I'm posting stuff in the textbook, I'm sort of narrowing down the concepts. I got my own diagrams, I'm trying to conceptualize the assignment and verifying the accuracy of it. And then I have it explain the concepts, sort of giving me suggestions on which route to take. And finally, just some help with final sort of debugging. That goes on for a while. And then I had sort of accuracy check my script after I'd already proofread it, just to make sure I wasn't saying anything incorrect. So, the IPC method here uses the pipe. So we'll go back to the program. There it is. So the child, just to get to the mechanics of the little pipe, the pipe is created here. It's a special array with two indexes, the read and the write end. 0 is read, 1 is write. Each child first closes the read end of the pipe. It does its thing. It writes the result to the pipe within the little message struct in its time, and the index indicating which of the functions in this array was the one that was called. I just printed a little summary of whatever function was called. After it writes, it closes the right end of the pipe and exits so it doesn't fall through the rest of the program. And then back in the parent, we close the right end of the pipe. We read all the messages from the pipe, doing a little checking to make sure that there are no errors here. We put them in a result array. This is just long longs that have been calculated by the children. We then close the read end of the pipe because we're all done reading and writing. After we process the results and read them and process them, we reap all the children to avoid zombies. And then we finally get the ending time of the parent. We print the results. The parent prints the results, and then we print the parent's time just to compare with the children's time to verify parallel execution. And we finally have a final message confirming the parent's PID is the same as the one at the beginning, showing that it was running all throughout. I believe that concludes my video. Thank you very much for watching.